pressure measurements have a wide variety of applications. They can be used in measuring the difference in pressure between valves on a test stand system, or on the outside of an airplane or aircraft, or even in kitchen appliances. You know, you have a pressure cooker at home. So this lab specifically is going to focus on the difference in calculating pressure, the difference in pressure measurements between a polycarbonate cylinder and a soda can. So really quick, I'm going to get into the lab overview, and this is going to kind of outline what we're going to be talking about today, and my other lab members will talk on it too. So really quick, what is the objective of this lab? To measure the pressure in a polycarbonate cylinder and a soda can using a Wheatstone bridge and a strain gauge. So one of the things to note here is that we do change the difference in configuration of the Wheatstone bridge depending on what we're measuring. We use a full bridge for the polycarbonate cylinder and a quarter bridge for the soda can. Another thing that we're going to be highly monitoring is the random error versus systematic error, and what kind of values play into what, and which one do we see to basically have a higher significance in this case. And then another thing that we're going to be looking at is the relationship between strain and pressure readings and how those two compare. So between the soda can and between the polycarbonate cylinder, and seeing how accurate the Wheatstone bridge's configurations are. I'm going to hand it off to Anna, and she's going to talk a little bit about the introduction.
Hi, I'm Anna, and I'll be talking a little bit more in depth about pressure. Pressure is described as the normal force exerted by the matter per unit surface of the plane. Cylindrical pressure vessels, as we can see in the picture, experience both longitudinal and hoop stress. And the relationship that describes the longitudinal and hoop stress is right there. And you can see based on the equations that hoop stress is twice the amount of longitudinal stress. Therefore, it is very important for us to measure hoop stress, because when a pressure vessel bursts, it's usually because of the hoop stress and not the longitudinal stress. Now, there are two pressure sensing methodologies. We have mechanical pressure gauges and electromechanical pressure gauges. In this experiment, we used both. For the mechanical pressure gauges, the deflection created by the sensing element is read directly by a dial or a pointer. In this lab, we used a Bourbon gauge, which converts the pressure difference to angular displacement. For the electromechanical pressure sensors, the applied pressure is converted to an electric signal. In this lab, we used a strain gauge, which is depicted in the image right there. And how it works is it consists of a flexible backing, and the flexible backing supports a metallic foil pattern. The metallic foil pattern is the yellow part of the figure, and as the object is deformed, strain is applied to the object, the foil is deformed. Now, due to the deformation of the foil, the resistance of the foil changes. So tension causes resistance to increase, and compression causes resistance to decrease. The resistance change is commonly measured using a Wheatstone bridge. What is a Wheatstone bridge? A Wheatstone bridge that looks like that is an electrical circuit, and in the picture we have depicted a quarter Wheatstone bridge, which means that one of the four arms is a strain gauge. In a half bridge, we would have two of them be strain gauges, and in a full bridge, we'd have all of them be strain gauges. What they do is they measure overall resistance change over time, with the output being the voltage output, and they also increase sensitivity and reduce the effects of temperature on the system. Now I'm going to pass it on to the procedure.
My name is Corbin Mayer. I'll be discussing the materials and procedure section for lab number 4. And first and foremost, I'll be going over all the materials used for the lab. First, we used some strain gauges. We also had a polycarbonate pressure vessel. We used a computer with LabVIEW to take the measurements. For a secondary experiment, we also had a 12-ounce soda can. We had sandpaper and super glue, as well as an NI DAC system. Next, what we have is the polycarbonate cylinder, which was pressurized using air in increments of 5 psi from 0 to 30 psi. The information was collected using a full Wheatstone bridge strain configuration. As can be seen here, we use 4 strain gauges, 2 in the hoop direction, 2 in the axial strain direction. And this allows for the isolation of hoop strain using the Poisson ratio. For the second experiment, we used a soda can, which was sanded down bare to reveal the aluminum surface, and a strain gauge was attached using tape in the hoop direction. And after this was all completed and it was subbed to the quarter Wheatstone bridge, what we used to measure the pressure difference, we opened the pop tab on the can and got the data from the relief pressure. Right here is the quarter bridge strain gauge configuration, which measures the hoop strain. It does not isolate hoop strain, as the strain gauge is susceptible to axial strain as well.
Moving on, we'll be talking about the results from our lab 4. So, as Corbin just mentioned, the first part of our lab involved taking a polycarbonate cylinder and pressurizing it at different pressure values and measuring strain. But of course, we can't just get strain and pressure immediately. What we get first is our raw voltage. So presented here is a table and a graph describing our raw voltage as a function of our pressure gauge pressures. So we have to take this raw voltage and find strain and pressure somehow. So here's how we do that. The first thing we have to do is balance our strain gauge. That involves balance our Wheatstone bridge, and that involves finding a balanced voltage. So here's the formula for that. And what do these values mean? So the voltage strained, or V strained, is the raw voltage that we found in our experiment, and the V unstrained, or voltage unstrained, is the voltage value at 0 strain. In this case, we know what that value is because we have a strain measurement from 0 psi, which corresponds to 0 strain. So presented here is a table and a graph of our balance voltage versus gauge pressure, and you can see that our voltage increases as a function of gauge pressure, which is correct, because as you see more pressure, therefore more strain, you should have a higher voltage differential between the 2 branches of the Wheatstone bridge. So the next few steps we have to do to get to strain are as follows. First, we find a V out using this formula, a voltage ratio between the voltage in and the voltage out, and finally a strain value that you find using this formula. An important thing to note here is that this formula involves the Poisson ratio, and as Corbin mentioned earlier, in a full bridge strain configuration as the one we used in this case. You have 2 strain gauges in the hoop direction, 2 in the axial, and you want to decouple hoop strain from axial strain, and you do that by using the Poisson ratio. Finally, here's a graph of our strain. As expected, strain goes up as pressure goes up. That makes sense. As you pressurize the vessel, you experience more deformation. So finally, we want to find the pressure. You do that with this equation, and the results are given here. So the pressure that we found from these strain values are given as theoretical pressure, and the gauge pressure that we saw on the actual dial are given as gauge pressure, and the percent deviation is shown here. So now let's graph these values and take a look at how they compare. So as we can see, these values are pretty close, indicating a relatively high accuracy. There doesn't seem to be a huge systematic error, as the points aren't consistently below or above each other. But there is a little bit of random error as the points aren't exactly aligned, and this is probably because of human error. We could have misread the pressure gauge. It won't be exactly at 30 or 5 psi. And we saw during the experiment the gauge wouldn't necessarily consistently hold pressure. It would fluctuate up and down, so that could also be a source of error. But overall, our points look pretty good. They are pretty similar. So the second part of the experiment involved taking strain gauge measurements from a soda can that we opened. Again, the first thing we did wasn't just find the strain. We had to find raw and balanced voltage. They are given here and here. One thing to note here is that the graphs are essentially inverted versions of each other, and that's because the balanced voltage is really the only one that matters. For the raw voltage, we see that voltage goes up into around the 1 millivolt area, and the balanced voltage comes down. That's because our unstrained case here, the one with 0 strain, is right at the very end when we open the soda can, and then all the fizz come out. And so when we do that subtraction, we just inverted the graph. So the first three parts here are the same as the polycarbonate cylinder, but the last two differ slightly. Since we're doing a quarter bridge strain configuration here, we don't have to worry about the Poisson ratio for the hoop strain. And the pressure, it's a pretty simple formula, but it is slightly different because, again, we're working with quarter bridge and not full bridge. And so finally, here are the strain versus time and pressure versus time graphs for the opening of the cannon. And we can see, as we expect, strain goes down since the pressure isn't pushing against the walls of the soda can, and obviously pressure goes down. That's what happens when you open a soda can. All the fizz and all the pressure comes out. So important conclusions we can make from this graph. The main one is that we know what the pressure of an unopened soda can at room temperature is, and it's around 52.55 psi. This fits with most literature values that suggest pressure is from around 50 to 70 psi for a room temperature soda can.
So, when talking about the conclusions, with both the full and quarter bridge Wheatstone bridge configurations, the strain gauge is measured, the changes in strain in each of the pressure vessels, and output a voltage which allows us to calculate both pressure vessels and hoop strain. So that's basically what this entire lab was, and this was the way we were able to come to these conclusions. So one of the first things that we were able to conclude was between the Wheatstone bridges when measuring strain and pressure for the full and quarter. And it seemed that the full bridge configuration seemed to give a more accurate reading because it's able to decouple the hoop strain. So it's able to just isolate the hoop strain and provide a more accurate reading there, while the quarter bridge wasn't, and it lumps axial hoop together. Another thing was that random error played a larger role than systematic error in indicating accuracy, and that's just because the random error calculated was higher than the systematic error, as Harsha had talked about on the graphs, and that just shows that the full bridge is pretty accurate, and it doesn't really say much about the quarter bridge. Another thing, the linear relationships between strain and pressure on both the polycarbonate cylinder and soda can, and more specifically, you could see how the strain increases as the pressure increases in the polycarbonate cylinder, and then pressure and strain also follow the same pattern in the soda can, which was also seen side by side with the pressure time graphs for the soda can and that last relationship. Another thing is that these results allow for an accurate selection of Wheatstone bridge configuration while measuring strain and leaning towards the full bridge configuration. And then, of course, our last piece of conclusion, and Harsha had just talked about it, but we were able to, accurately measure that the unopened pressure is around 52 psi. So that was just a conclusion of kind of everything that we talked about today. Thank you for listening, and yeah, that was Lab 4. Thank you for listening.